Okay, so what we're going to do now is we're going to talk about the Java ForkJoin Pool. And the Java ForkJoin Pool has been underlying almost everything we've done to this point related to parallelism and asynchrony in Java 8. So obviously we've talked before about parallel streams internals, and you got a little bit of an overview of the ForkJoin Pool. We've talked about completable futures, and I mentioned how it uses the ForkJoin Pool by default, although you can have your own pool if you want. You don't have to use the ForkJoin Pool. But the ForkJoin Pool is a very powerful part of Java. And so I'm going to talk here about how it's used in order to be able to process tasks in parallel. So now we're going to really kind of look at it more from the point of view of actually programming to the ForkJoin Pool APIs as opposed to encapsulating the ForkJoin Pool APIs under the parallel streams and completable futures APIs. So that's how you've seen it heretofore. So now we're finally at the point where we can kind of dig a little deeper and see how it works under the hood. So let's start off by talking about the style of programming that the ForkJoin Pool provides you. And I just absolutely love this animation. It's just so great because it really illustrates what's going on at some level. So the ForkJoin Pool is a style of parallel programming that solves big problems by divide and conquer, right? So it chops them up into smaller pieces. So that's the axe. And I managed to keep the wood metaphor going here a little bit. So you'll see some other wood stuff here in a second. I spent a lot of time trying to find these images. They're really fun. Hopefully it works the right brain of your mind as well as the left brain part. You know, you can see more holistically. So just a quick recap. You already know this, but I'm going to talk now about it in the context of the ForkJoin Pool, which is just a little different from how you've been exposed to it in the context of parallel streams. So the way this works is you have some data source, and you split the data source into chunks. These chunks are going to be tasks that are converted or transformed, split into subtasks. And that's a little bit different from the parallel stream stuff. Because remember, in parallel streams, you have the splitterator, and you split things up with try split, and then the things that are split up get passed off invisibly to you under the hood to the underlying ForkJoin Pool. But in this model, you have to do more of that splitting and joining explicitly. So you'll see in a second when we look at some code that you actually have to call fork, and you have to split things up and so on. And the way that you do this, the way that you create subtasks is by calling fork. We'll talk a lot more about fork, and I'll explain to you what fork does in just a minute. Now, this, of course, is another clever thing. We don't want to be splitting hairs, right? That would be bad. So if you end up with things that are really small, there's no point in splitting them any further. And so part of the challenge is to know when it makes sense to stop splitting stuff up. And there is no easy answer to that question. So you may have to do some experimentation in order to figure it out. Sometimes, see, when you use the parallel streams framework with the built-in Java collection framework collections, that decision is largely made for you because they already know how to split themselves. They may or may not split themselves optimally based on what your program is doing, but they will do it for you, and you have little or no control over it. When you program with the ForkJoin Pool framework, in contrast, you have to become responsible for knowing how to split things up. And that's good and bad. It gives you more control, but it also means you have more work to do. So once you've figured out how to split things up and fork them, then you have to solve the subtasks in parallel. And again, you'll see that unlike the parallel streams approach, where the way you program is by simply providing these behaviors, right? Lambda expressions, method references, and so on, and all that stuff just magically happens. With the ForkJoin Pool framework, you have to write the implementation that will compute these subtasks in parallel. And by and large, the method you call is called compute, and we'll talk more about that shortly. Obviously, the win here is that once you've split things up to the right optimally sized chunks, and then you run each of those chunks sequentially on all the different cores, right? So each chunk runs sequentially, each subtask runs sequentially, but all of them can run together on the cores. Then that's where you get your speed up, because all these things can run in parallel, and they're mapped to the cores in various kinds of ways. And obviously, if you have multi-core machine, it'll run in multiple cores. If you have a single core machine, then it'll have different threads under the hood, and they'll swipe, time swap and so on under the hood. Now, here's something that differs ever so much from the parallel streams approach. You have to explicitly wait for the results to complete. The results that are being computed serially in parallel will then have to explicitly be joined together, and you have to wait for them. And the way you do this is by calling a method called join. And so after everything's been forked, then you have to wait to join up the results. And you'll see that this is fairly straightforward, but there's some subtleties you have to be aware of. And if you get it wrong, your program will not run fast at all. It'll probably run slow. So you have to be a little bit cognizant of the way in which you join things together relative to the way in which you fork them. And then you end up merging the results. And in typical fashion, the way in which you merge is very similar to the way in which you join. So you kind of fork and join the things together. And the end result of all the merging and so on is that you end up with a single result, which is the result of the overall computation. Now, in some cases, there are no return results at all. And I'll show you an example of that either today or next time. And if that's the case, then join doesn't actually get a result back. It simply waits, and then when its subtask complete, it returns with no return value, and then you get the result back through some other means, typically a shared data structure that all the threads are working on without interfering with each other. And I've got a really cool example to show how that works later. All right, so that's just a quick overview of the computational model. Let's now talk a bit about internals. You've seen some of this before, but now that we're going to actually do an assignment with it, you may want to pay more attention because it's more interesting at this point. So a ForkJoin pool is essentially an implementation of the so-called executor service interface. So ForkJoin Pool is a class, and you can read about it here, and it's very interesting. There are a bunch of other implementations of the executor service. So you can see that the executor service is an interface that implements something called executor. If you take next semester's class, you'll learn more about all this stuff. There's this class called abstract executor service that implements the executor service and provides skeletal implementation for a lot of the pieces. And then there's several other classes that inherit either directly or indirectly from abstract executor service. There's thread pool executor, so there's fixed sized and cached thread pools. There's this thing called a scheduled thread pool executor, which basically uses timeouts to do things based on time. And we have our good friend ForkJoin Pool, which, as you can see, also inherits from abstract executor service. Despite the fact that these things all implement the executor service and the abstract executor service, they're actually quite a bit different. So there's some things that are similar, some things that are different. We'll talk about that. One of the most obvious differences here, of course, is the ForkJoin Pool runs ForkJoin Task, whereas the thread pool executor and the scheduled thread pool executor do not run ForkJoin Tasks. Well, obviously, that begs an important question. What the heck is a ForkJoin Task? So a ForkJoin Task is a chunk of data that you control, that you manipulate, you create, you manage, along with some functionality to do stuff on that data. And we'll see it's kind of the basic unit of scheduling and computation in the ForkJoin Pool framework. And there's a bunch of methods that a ForkJoin task has, but the most important of them are fork and join, as you might expect. And here's kind of how to think about this. So fork, as you can see here, if you are a parent class, then when you call fork, you arrange to asynchronously execute this task in the appropriate pool. So fork doesn't start running the thing right away. It simply says, put me in a queue that, when the time is right, will be used to run this task in parallel. And we'll talk a bit more about that in a second. So that's what fork does. And you can see here, you can have, a parent ForkJoin task can recursively spawn a bunch of child ForkJoin tasks by forking them. And then at some point, after you've forked them all off, and they're all running or getting ready to run, then you can no longer make any progress until all your subtasks have finished. So now you're going to have to wait for them to finish. And the way you wait for them to finish is by calling join. And what join does is it returns the result of the computation when the computation is done. So again, assuming we've forked these guys here, then after they're off and running, then the parent task eventually says, okay, I've forked enough as I can, and now I'm going to have to wait for the results, and I'm going to join with the things I've forked. And join does really does two things. One thing it does is it waits for the result, and it also gets the result, right? So sometimes those are one and the same. You wait for the result and you get a result. Sometimes, as I mentioned, there is no result, so you're simply waiting for the subtask or subtask to finish, and you'll get the result some other way. But that's the basic idea of fork and join. It's a very simple model, but there's all kinds of really cool things that they can do to optimize it under the hood. So one of the things to remember is that a ForkJoin task is not a thread. In other words, it doesn't have its own runtime stack. You can't actually schedule a ForkJoin task on a core. Instead, you can take a bunch of ForkJoin tasks, and we'll see how they're managed in a minute, and you can queue them up in clever ways, and then you can have a pool of threads, these guys, the big honking steroid Java threads that really have their own stack and their own ability to run on their own core and so on and so forth. And these threads, of which there are few, will run these ForkJoin tasks, of which there can be many, many, many. So we can have, hundreds or thousands or tens of thousands maybe of ForkJoin tasks that are all being multiplexed over a much smaller number of Java threads. And you can read an article, a nice article by my buddy Doug Lee, who wrote all this stuff, and he gives you an overview of why they do it this way. And the basic reason for doing this is they want to keep these threads, which are ultimately mapped to cores, they want to keep these things as busy as they possibly can. So they want to have all this work up here so that whenever a thread has got a spare cycle to run, it can grab the next available the next available ForkJoin task and go to town on it. And it can also, if it's implemented cleverly, which it is, of course, because Doug's a smart guy, he arranges to make sure that these threads in the pool of worker threads balance their processing using all the different ForkJoin tasks that are waiting to run. Any questions about that? So the whole name of the game here is balancing the processing. Programs almost never use ForkJoin tasks directly, although there are some clever things you can do if you program in such a way where you can access other things through a ForkJoin task interface. Instead, they extend and implement one of its subclasses. Most commonly for our purposes, it'll be this thing called Recursive Task. So we'll see that Recursive Task is what we'll use and what you'll end up using. And that is a subclass of ForkJoin Task. And Recursive Task, as we'll see maybe now, maybe next time, adds some additional stuff to make it easier to write the code for doing the ForkJoin Task stuff. There's also other thing called a recursive action, which doesn't have a return value, and then something else called a counted completer, which is actually used extensively throughout the Java parallel streams framework, and we're not going to talk at all about that. It's much more complicated and harder to motivate the need for it, but it's really cool. If you want to have your mind just sort of melt, read the documentation for counted completer. It's very cool. Okay, let's talk a little bit now about how the ForkJoin pool works under the hood. I've mentioned this before, but I think it'll make more sense now because you're getting into hopefully the paradigm a bit more thoroughly. So keep in mind, we've got this pool of worker threads, and those are fixed at any given point in time, but as you learned by using managed blocker or changing the properties or some other means that we'll talk about, you can make the number of threads expand or contract, right? So the pool of worker threads could grow or shrink. Let's assume, just for sake of argument for a moment, that they're fixed. It makes it easier to talk about. So each of these threads here, whether they're fixed or growing or shrinking, each of them is associated with something called a DEC, which is a double-ended queue. And it's a circular data structure. And the way it works is whenever you call fork, whenever you say, bloppity blop fork on your instance of recursive task or counted completer or recursive action or ForkJoin task or whatever it is you're using to make your computation, whenever you say fork, that takes the new task, which is now really a subtask, and it pushes it onto the head of its DEC. Remember, every thread in the thread pool has its own DEC. So it pushes the subtask onto its DEC. Now, after it does fork, then at some point it's probably going to say compute. It's going to say do some work. And at that point, that same thread will then turn around and, under the hood, pop the next task from its deck and then go ahead and compute it. It'll say compute or whatever it's going to do to run it. So the key thing to note here is that fork pushes at the head, and when you compute, if you don't have a task, the ForkJoin Pool under the hood will pop the item from the head. So whatever you just put is the same thing you're going to get out. So it's a LIFO structure, last in, first out. Why is it done that way? This is really important to remember. It does it this way so that it maximizes locality of reference and improves cache performance, because the thing you're about to work on is probably something you just put there, so chances are the data and any computation you're going to run is fresh and ready to go in the cache. So that makes it super fast. So when you put something on the deck, you can put a bunch of things on the deck. You can say fork, 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 and when you say compute, it'll then go ahead and pop the item off and start to run. Now, here's an interesting thing, and you'll see this when we have the time to go through the example code here, which is now looking like it's going to be Monday. It's super cool. What happens is, if you have one thread that's putting a bunch of things onto its deck, you might ask, how the heck do the other threads get a chance to run? Because this one thread did fork, 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 and then, I've already told you there's a bunch of other threads sitting around waiting, but those guys don't have anything in their decks because one thread was doing all the forking. Well, what happens to make this work, and it's really cool, is this idea of work stealing. So if you have other threads in the pool and they don't have anything in their decks at all, then what they'll do, like let's say that they've gotten to the point where one thread discovers his deck is empty. He's not playing with a full deck, as they say. He's going to go ahead and steal a subtask from somebody else's deck. And that somebody else's deck is selected at random to try to avoid bottlenecks. But a deck is chosen at random, and the idle thread will steal work from the tail of another thread that has stuff on its queue. And that, of course, also begs the question, why does it steal from the tail? And the reason it steals from the tail, of course, is that by doing this, the implementation can have a lock that protects the tail and a lock that protects the head. And as long as this thread is doing stuff only to its head, this thread can be pulling stuff off of its tail, and these two threads will not be contending with each other. There will be no lock contention. They don't have to worry about blocking or waiting or synchronizing. They'll just go in and say, aha, I get the lock, nobody else is using it, I get the item, I release the lock, boom, it's super fast. And so under the hood, they use really fast spin locks or these wait-free locks that use so-called compare and swap operations to do the synchronized access to the deck super fast with minimal contention. So again, as long as one thread is doing stuff on its head and another thread is pulling stuff off its tail, they don't contend. Of course, if you have multiple threads all trying to pull stuff off the same deck's tail, they will contend. If briefly, they will contend. And that's why the ForkJoin Pool tries to randomly steal things from other threads' decks, so that way they probably won't be trying to steal from the same deck, which is good. Any questions about that, Peyton? Yeah, because circular deck allows you to do things efficiently at the beginning and end without having to traverse through the whole list. So it's a clever trick you typically do in data structures world where you make the thing circular, so there's sort of no beginning and end. Well, there is a beginning and an end, but the whole thing is really efficient to do without having to ever have like empty nodes or without having to search through the whole queue. You can get to the beginning and the end easily. So this circular deck lowers contention. And if you take a look here at this paper, it'll explain all the gory details of what they use as the implementation for this. It's actually a very simple idea, but it's a very cool idea. And it's something that's used very heavily, not only in Java, but in all the other JVM-based languages that rely on the Java virtual machine, such as Scala and other frameworks like RxJava and other things. Okay, So there's a static common pool, I think Matt mentioned this earlier, that's available and useful for most applications. And there's a method called common pool that's static, as you can see. And there's one, of course, because it's static, there's one of them. There's one common pool. And this is used by any ForkJoin task that doesn't explicitly submit to a specific pool. So if you're not explicitly submitting a task to a specified pool, it uses the common pool. And I think we've talked about this before. The reason for doing this is that this allows the system to more globally optimize the core management of the system with the goal of trying to keep the cores as busy as possible because we want them to do their job. Cores exist for one thing and one thing only, to process, right? They don't want to sit there and be idle. Now, this common pool size can be expanded and contracted programmatically. So you can think of inflating things, right? One way to do this is by modifying this system property, java.util.concurrent.forkjoinpool.comma.parallelism. So you can set this to whatever value you want to set it to. But that's a manual thing to do. So it's kind of like manually blowing up a balloon. And you get winded after a while if you do that too much. The other downside is that this will affect all the usage of the common ForkJoin pool in a process. So if you make a change in one part of your process, then that will have the side effect of changing the size for anything else in the process that's using that. And that ripple effect may be confusing and undesirable. Therefore, we need to have some way of automatically increasing the ForkJoin pool size. We don't want to use the manual approach all the time. So the way to do that, as I've talked about before, is by using a managed blocker, and that can be automatically used to inflate and contract, expand and contract the ForkJoin pool. And I just want you to know I spent a lot of time finding these pictures of balloons, so I hope you appreciate them. Right? So the metaphor of manually inflating it by setting those things or using a machine to do it for you. So these temporarily add the worker threads to the common ForkJoin pool, and then under the hood, this will reclaim the threads when they're not being used, and then reinstate them, reincarnate them later when they're needed to be used for some other purpose. Okay, that is probably a good place to